Hello all, Deepesh here. Today, let's talk about leveraging cache for performance and security. This is going to blow your mind. In the world of computers, speed is king. Every millisecond counts when it comes to processing data and executing tasks. Like a bustling city, data flows constantly between the processor, memory, and storage. This continuous flow is essential for the smooth operation of any system. But accessing main memory takes time, creating a bottleneck. This delay can slow down the entire system, much like a traffic jam in a busy city. This is where cache memory comes in, acting as a high-speed messenger between the processor and memory. Imagine a library where frequently accessed books are kept on a special shelf for quick retrieval. Frequently accessed books are kept on a special shelf for quick retrieval. This makes it easier and faster for people to find what they need without searching through the entire library. Similarly, cache stores frequently use data and instructions, allowing the processor to access them rapidly. This reduces the time it takes to fetch data from the main memory. There are different levels of cache, L1, L2, and L3. Each level serves a specific purpose and has its own speed and size characteristics. L1 is the smallest and fastest, while L3 is the largest and slowest. L1 cache is closest to the processor, providing the quickest access to data. L2 and L3 caches are crucial for performance. They act as larger storage areas that hold data not immediately needed, but likely to be used soon. They act as intermediaries, holding data that might be needed soon, reducing the need to fetch it from the slower main memory. This layered approach ensures that the processor can work efficiently. When the processor needs data, it first checks the cache. This initial check can save valuable time and resources. If the data is there, it's a cache hit, resulting in a faster operation. The processor can quickly proceed with its tasks without delay. If not, it's a cache miss, and the processor has to wait for the data to be retrieved from main memory. This waiting period can slow down the overall performance. Effective use of cache can significantly boost performance. By reducing the time needed to access data, the system can run more smoothly and efficiently. By understanding how data is accessed and stored, developers can optimize their code to maximize cache hits and minimize cache misses, leading to faster execution times and a smoother user experience. This optimization is key to achieving high performance in modern computing systems. Arrays are fundamental data structures in computer science, serving as the backbone for many algorithms and applications. They store elements of the same data type in contiguous memory locations, like houses on a street, each with its own address. This sequential organization makes arrays very cache-friendly, enhancing the speed of data retrieval. When an element of an array is accessed, nearby elements are also loaded into the cache, thanks to the principle of spatial locality. This is because of spatial locality, the concept that data close together in memory is likely to be accessed together, making subsequent accesses faster. So, if the program needs to access the next element in the array, it's likely already in the cache, resulting in a cache hit and faster processing. However, arrays have limitations that must be considered. Their fixed size can lead to wasted memory if not all elements are used, causing inefficiencies in memory utilization. Inserting or deleting elements in the middle of an array can be inefficient, requiring shifting of subsequent elements, which can be time-consuming. Despite these drawbacks, arrays are powerful tools for performance optimization, especially when dealing with predictable data patterns. Their cache efficiency makes them ideal for storing and processing large amounts of sequential data, such as images, audio, and video, where quick access is crucial for performance. Unlike arrays, linked lists store elements in non-contiguous memory locations, which means that the elements are scattered throughout the memory. Each element, or node, contains a pointer to the next node, forming a chain-like structure that links all the elements together. This flexibility allows for dynamic resizing and efficient insertion and deletion of elements, making linked lists highly adaptable to changing data. However, this flexibility comes at a cost. Cache efficiency can be significantly impacted. Since elements are scattered in memory, accessing one element doesn't guarantee that nearby elements will be in the cache, leading to inefficiencies. This can lead to more cache misses, slowing down processing and reducing overall performance. Interestingly, this non-contiguous nature offers a security advantage by making it harder for attackers. Exploiting vulnerabilities often involves manipulating adjacent memory locations, which is more challenging with linked lists. Linked lists, with their scattered elements, make such attacks more difficult, enhancing security. Choosing between arrays and linked lists depends on the specific application and the requirements of the task at hand. Arrays excel in performance-critical scenarios with sequential data access, providing faster processing times. Linked lists shine when flexibility and security are paramount, even at the cost of some performance overhead, making them ideal for certain use cases.